Within the next slide, I want to present the main results, and I start with the results we have regarding hardware. At the beginning of the project, a wireless tracking system based on surface acoustic waves, SAW, was tested with a suitable antenna which is attached to the ladle, and a reader consisting of reading unit and antenna, which is reading out the signals of the sensor. The advantage of this system is that it's insensitive to dust and smoke. It can withstand temperatures up to 400 degrees Celsius, and it is insensitive to electromagnetic field of the electric arc furnace. Nevertheless, there are some disadvantages. For example, that the system is sensitive to other WLAN sources in the same frequency of 2.4 gigahertz, and that the range and lifetime of the SOV sensor decrease with increasing temperature, like they are at the steelmaking ladle. We have performed trials within laboratory and steel plant, and found out that this system does not fully meet the process requirements at the steel plant of Feno due to difficulties in technical feasibility for realizing all readout stations that would be necessary to cover the process, and due to high follow-up costs for SRV tags and maintenance during operation, because at Feno, due to the movement of the ladle and turning, each ladle would have been necessary to equip with 2 sensors or tags. Thus, an alternative solution for wireless tracking of steelmaking ladles with a customized camera-based system was installed or developed. 6 visual cameras and 1 infrared camera, including protection, were installed throughout the process of Feno, covering all positions from electric arc furnace, ladle furnace treatment, casting, and maintenance to maintenance positions. All ladles were equipped with individual plates for a unique identification. And throughout the project, several improvement of the plates and alignment, respectively, the protection of cameras was performed. I will also say some words about this at the end or later. Regarding software, a new database infrastructure was established at Ferriere Nord, consisting of the data or the ladle tracking system, the data from the ladle tracking system, a selection of relevant level 2 data, as well as the thermal measurements of the ladle shell temperature done by the infrared camera. A tracking software and a new interface were developed and installed on the server of Ferriere Nord to display graphically the positions of all ladles, as well as their predicted aging or wear status, which is done by coloring the ladles, and to provide detailed information about ladle and actual heats, as well as previous heats, by clicking on a ladle. Additionally, an interface was realized that connects to a database that exchanges the necessary data with an algorithm for predicting the aging status of the ladle. This ladle utilization optimization tool uses AI-based technologies and the platform for analyzing the ladle data that is coming from the level 2 database, for example, number of heats, and the data from the thermal database, which are the measurement data of the infrared camera. This will be presented by Marco after my presentation. And last but not least, a simulation engine based on a discrete event model was developed to optimize ladle logistics, and this topic will be presented by Setik later this morning. These tools that were developed within the Tracker project allow to optimize the production processes, not only the one of liquid steel production, and in this case to avoid ladle mix-up. They also are enabling to avoid a breakthrough of the ladle being strictly related to security matters, productivity, and costs. They can help to increase the life usage of a ladle and for proper management of the ladle focused on its refractories. Thus, the overall industrial and socio-economic impact reduced material consumption and reduced energy consumption, as well as increased safety. As I said, during the project, there were several optimization actions necessary. For example, the analysis of first experiences of tracking data and additional measurement data, for example, internal camera temperature, revealed issues regarding accumulated heat at the infrared camera due to a very close position to the hot ladle in the plant, dust forming a sticky layer on the cameras at the casting positions, and insufficient pattern recognition due to inhomogeneities on the plates. The optimization of the system included, for example, improved camera cooling via additional heat protection, course analysis regarding the dust layer formation, and suggestions to avoid it by not blowing all the time, but just temporarily. They included a new design for plates attached to the ladles, an improved use of level 2 data for tracking the ladle at the positions where no camera is available, a change of camera positions for a better angle and view to the plate, and a better management of data signals. To sum up regarding hardware, I can say that the trials with the SOA sensor revealed a maximum distance of 4.40 meters to realize at the Pheno steel plant. As I mentioned, this can be different depending on the surrounding conditions for each steel plant. The camera-based solution with plates was implemented and optimized. Temperatures at the optical cameras were decreased to be between 35 and 50 degrees Celsius, depending on the position where the camera is located. The active cooling of the infrared camera has reduced temperatures from about 50 degrees Celsius down to 35 degrees Celsius. We evaluated the performance of the system and found two kind of errors that I mention here. The one is regarding availability of camera information, and the other one is regarding incorrect ladle recognition during another treatment. The first errors were summed up to be about 23 or even 92%, depending on the ladle which was chosen in 2020, which is about the middle of the project, which was at the middle of the project. At the end of the project, those errors were reduced to be about 5.5 or 5%. The errors regarding incorrect ladle recognition while another running treatment was done summed up to be about 3.5% and 2.5% in 2020. In heats chosen from 2021, this error did not occur at all. Also, the replacement of a full plate due to severe damages has not yet occurred. This is most likely due to two reasons. The one is that the plates are installed at the ladle handle or at positions where they are not exposed too much, and due to the very stable mechanical construction of the plates. The tracking software provides useful information at one glance and one moment, giving an overview of the whole ladles regarding the positions and the information. And thus it provides feedback to increase the security concerning ladle mix-up, potential steel leakages, reduction of faults due to mix-up, or the matter of recovery costs. The software is running stable, and writing and storing the data in the database tables is working well without problems. The ladle status prediction system developed by SSSA is able to correctly detect in advance more than 75% of the situations where maintenance operation is required on the ladles. And the optimization engine for ladle logistics was identified, developed, and tested with data from the Ferrera Nord steel plant and is deployed at the CITIC servers. Last but not least, I would like to say some words about exploitation. As I mentioned, the tracking system was successfully installed, commissioned, and optimized for the consistent factory-wide tracking of the ladles in the steel plant of Ferrera Nord in Osopo. All components remain working beyond the project and support the Fino staff in monitoring the steel production processes, in collecting and analyzing tracking data of the ladles, and in advising the operators regarding ladle handling. The tracking system could be transferred also to other parts of the steel production, for example, for tracking tundishes or slack pots, but also to other production processes. The TrackOpt software of BFI was developed in a modular way so that an extension and or a transfer to other plants is possible at any time. The SSSA tool for the AI-based prediction of the ladle status is designed to be transferable to other plants if suitable information is collected. And the simulation engine that CETIC has developed within the project is already being applied in a regional research project regarding the sizing of sterilization facilities. So I am at the end of my short presentation to give an overview of the TrackUp project. I thank you for your attention. If you have any questions, I think we have a few minutes, to answer.
Thank you, Birgit. This is Debbie Ogren from Uddeholm. I would like to ask, is there a limit to the number of ladles that can be used in the tracking system, that can be tracked in the system, minimum, maximum? Yeah.
No. The system is adaptable and can be used for more or less ladles or whatever wants to be tracked. As I said, at Fino Plant 5 are in operation at the same time, and you could see maybe here five are colored and are in operation. The other ones are outside and offline. And as long as all ladles are equipped with a plate and the cameras are positioned, we can track any number of ladles.
Thank you.
You're welcome.
So, Herbert Köchner from KTH. Maybe I have one question regarding the availability. You mentioned at the end of the project that there were 5% when there was no availability on the ladle number. So I assume that this is that during the cycle, in 5% of the cases, that not at all positions this was available.
We analyzed the two ladles within the times, one in 2020 or two in 2020 and two in 2021, and we have looked at the whole life of each ladle from the first heat to the last one, and within these heats about 5.5% or 5% the data was not available, either at it could be it summed up at some position at the beginning. As we see here, for example, the high number, there was one main problem with one position where the ladle was not recognized, but it can also be at different positions. But during this high number of not available data, it was a problem of reading the plates at one position.
And at the end, what is, let's say, the main cause, or can you did you identify something about what is the remaining 5%?
It could be a problem. What we have not done is to add lightning, for example. So we are just using the normal conditions which are in the steel plant. Maybe a bit more increase of these detection could be possible by adding lightning at at some positions. But yeah, I guess it's mainly the recognition. It's not anymore the data availability, because there were also some problems within the project to get the data from the tracking system into the database. This problem or these problems were solved, so it's mainly a recognition problem, and I assume by adding lightning or lights or additional conditions could be improved.
Okay, thank you very much.
You're welcome.
Okay, if there are no other questions for Betty, before we go on with the Marco Vannucci presentation, I want to inform that we are recording the webinar. So at the end, I will be glad to share the link for a replay, and also the presentation will be available on PowerPoint or PDF format. So I will send you an email at the end of the webinar. So Marco, I let you share your presentation.
So can you see it in the presentation mode or the presenter mode?
It's in presentation mode.
Yeah. Okay, so I will try to keep my webcam on, and if it crashes, because I have experienced many times with Teams this kind of problem, I will switch it off. By the way, my name is Marco Vannucci. I am a researcher of Scuola Superiore Sant'Anna in Pisa in Italy, and I took part to the TrackOpt project. Today, I will show you the main part of Scuola Superiore Sant'Anna work within this project with this presentation entitled Predictive Maintenance of Ladles in Electric Steel Plants Through Artificial Intelligence. Here is an outline about this talk to better understand how it is related to the title of this workshop, Solution for the Optimization of Steel Plant. And the focus here is in the optimization of the ladle usage within the electrical route for steel production. I will try first to describe the problem we are facing and our basic idea for the estimation of the ladle aging. The basic idea that is developed by means of artificial intelligence techniques, starting from the collection and the management of data, the design of a model for ladle aging, and some tests that show how it works for real. Finally, we will try to wrap everything, look at the cost and advantages of this solution, and draw the main lines for eventual future of this approach. So this picture showed the context of this work. It is the production of steel through the electric route, a route which is sustainable from the economic and the environmental point of view, since it is based on the recycling of the steel, which is melted in a first step in the electrical furnace by using electricity. This operation produces liquid steel that is then collected for transport into a container which is called ladle. Then the ladle moves from the EAF to the ladle furnace, where another phase of the process take place, and where the liquid steel is refined. Finally, it moves to the continuous casting machine, where the steel is cast and the semi-finished product is obtained. And here comes our problem. Because the iteration of this cycle deposit progressively liquid steel on the surface of the ladle, on the internal surface of the ladle, affecting the effect of the LF process, thus the quality of the steel and the energy consumption. For this reason, there is an expert operator that evaluates the status of the ladle at the end of this path and decides whether to perform some maintenance on the ladle or keep it in the cycle. And consider that at Ferriere Nord, where this system was developed, was put into practice, there are 10 ladles, 5 of which are constantly operating. Currently, this decision, the decision of the expert on whether to maintain or keep there the ladle, is taken by an expert. So this decision is taken by a human operator that monitors the process while data are collected and in any case stored in a database. And this decision is subjective. And I mean, all the data are collected about all information about the production and about the maintenance activities that are performed on the different ladles. What is in this case the risk of a wrong decision? If maintenance is neglected, there is a product quality downgrade, and it is also dangerous. On the other hand, too many maintenance cycles means more money and a lower productivity, because while in maintenance, the ladle is not operating. And here we completely rely on that guy in the picture, our expert. Good to have it, but his decisions are affected by the subjectivity, his personal experience, and his tiredness, for instance. So the question is, can we take the same decision or even a better one of our expert, but more objective, maybe exploiting some information the expert cannot handle, and in the same time exploit his knowledge that he put through time into the database? So what we try to do is to use an artificial intelligence-based decision support system in order to improve the estimation of the ladle status. So the question is, does the ladle need to be maintained now at the end of this cycle? This tool that we developed predicts such status by using the same process data used by human operators and exploits for its tuning all the historical data collected during production, and that include also the decision taken in the past by the human operators. So on one hand, we have all the data collected and eventually some more information that are fed to the artificial intelligence tool. And our artificial intelligence tool exploits the historical data collected during the production in the past year, months, and tries to mimic the behavior of our expert, and we can say to learn his behavior. So what does the TrackOpt project brought on board to put up this system? New sensors, thermocameras that provide information about the ladle status and its internal coating that changes the way the heat propagates to the outer surface of the ladle. Thermocamera is the thing from the picture that you see in this slide that Predator uses in the Hollywood movies with Schwarzenegger. Then we have a new efficient tracking system about ladle position and process condition. It is new data that are fed to the informative system of the plant. And now it's up to you to mix this new information with other knowledge sources. So what are these data? They include a level 2 database that collects a wide set of information regarding the process and the still, among which temperature, process direction, injected gas, and the training dataset used for learning the behavior of our expert includes more than 3,000 ladle operations. So you see that more in detail, this level 2 database includes the duration of the tapping, the duration of the LF process, the starting and final temperatures of the LF process, the amount of injected argon, and so on. But we also have some additional information, which is the reading of the thermocameras. We have these thermocameras that point at two different regions, two regions of interest, the ROI, of the ladle on the external surface of the ladle during the LF process. These regions of interest were selected by the expert plant managers, and the measured temperature are considered significant for the ladle status. These temperatures are read every 5 minutes, and we have around 24,000 samples that are used for the training of our model. And it is what we get. These are the temperatures measured by the thermocamera during standard operation of the ladle for both the ROIs. The red or vertical dashed lines are the maintenance cycle. We see that there is an overall trend throughout the life of the ladle, but there is also a lot of noise. And this trend is not so clear between two consecutive maintenance cycles. The sensation here is that there is knowledge to exploit in this data, but we need to extract it, to refine it, including some pre-processing. Now let's see what kind of pre-processing we did. First, we applied an outlier detection method. This method was developed by within our labs in the last year. This method is multidimensional, and it was designed for coping with industrial data and based on fuzzy inference. Among outliers detection method, there is no method that overcomes clearly the other, but some that in certain conditions work better than the others. Our idea is to mix these methods, identify the situation, to exploit their good characteristics and maximize the results. After using this method of our data, the 3% of the observation gathered so far, so including thermocameras reading and level 2 data, were cut off. Secondly, some data synchronization was performed since the two employed dataset, thermocameras and level 2, use different indexing. The first one based on time, the second one on the heat ID. So we did some work here. Finally, some features were extracted. They include from the original data, from the raw data, because we saw that there was a lot of noise. Some features were extracted. They include median, standard deviation, averages of the thermocamera temperature, the difference between the temperature measured at the two regions of interest, LF process duration. All these features were selected to be robust to the noise that we see affect the original signal. And this is the core of the information that is later fed to the predictor of the status of the ladle. But are these features related to ladle aging? Are these features related to the end of the life, so to the need of a maintenance cycle of the ladle? Well, for some of them, it is quite clear. These pictures refer to what happens between two maintenance cycles. So in the top left picture, the delta, the difference between the temperature at the two ROIs, two region of interest, is clearly increases between two maintenance cycles. So it is something to keep into control. And on the bottom, we see that close to the end of life of the ladle, something happens at the region of interest 2 on the left, because it is the median of the temperature measured by the thermocamera in the second region of interest. And also in terms of the difference between the temperature at the beginning and at the end of the LF process. These are just some examples of the relation between the extracted features and the ladle age. So I put this slide here. We didn't talk so much about this within the project because it was one first attempt for monitoring the apparent age of the ladle, which was based on SOM. Here in this case, we use all the features that we extracted, so mainly process condition, to map the age. It is the part on the red box in this slide, and we use a SOM to map this multidimensional information into a small cluster. So to put together similar situation and to put a label, the label that you see in the picture on the right, which is the apparent age of the ladle. The SOM is used to map high-dimensional data into a lower space, normally in two-dimensional space, like in this case. And in our case, we map process variables. The nice thing about the SOM is that it preserves the distribution and the topology of original data. So it is very good for monitoring because close clusters here represent similar process situations. So during the monitoring, you can see this status changing, moving throughout this big square and reaching a final apparent age cluster where we see, okay, the ladle seems very old. Maybe it's time to make this maintenance cycle. But this idea was discarded because it was interesting for monitoring, but we had still many unreliable regions, so it was not very. The predictions were not very good. So we switched to another approach. What is our idea? Is to use these features as inputs to an artificial intelligence-based classifier in order to predict the latest status. Classifier means I give you a lot of information, this feature, and you decide, do I need maintenance? Yes. Do I need maintenance? No. In this context, all our historical data are used to train and evaluate two types of models. The first one is based on a decision tree, and the other one is based on a random forest, basically a group of decision trees that form really this forest. And in both these cases, The hyperparameters of these models were carefully optimized by using the available data in order to see which is the configuration that works better. So, but let's start by defining what the status of the ladle is. The ladle status in this work was discretized according to the classes shown in the pictures. In this picture, we represent the jobs of the different ladles, ladle A, B, and C, that occur one after the other. And we can see that, for instance, the 2 hits before the maintenance operations are considered end of life for the ladles, while the 5 previous to the end of life, so those in red, we can say that are the last 2 jobs before the maintenance, are considered end of life. Then we have another region, maybe 3 or 5 jobs in orange, that are considered pre-end of life. This is in order to discretize the different condition of the ladles. This discretization process was needed in order to use our data within the decision trees and the random forest. In any case, these alpha and beta that determine how many jobs are included in the end of life or in the pre-end of life are 2 parameters that are optimized together with the others within this job. So here is a short overview of the hyperparameters considered for the tuning of the decision tree and of the random forest. Among them, it is worth to note the class weight. This here, that is the cost, the penalty associated to the missed detection of an hit belonging to an arbitrary class. So what is the cost of wrongly classifying an end-of-life condition? Well, I expect it to be higher than the misclassification of a standard condition. The setting of these hyperparameters affect also the final results and the goodness of our tool. Among the others, we have the depth of the decision trees, how many levels, how many check among the features do we perform, and so on. It is a quite technical slide. In addition to what we have for decision trees, for random forest, we have how many trees are in the forest that form the forest, and this is the whole set of the hyperparameters tuned for optimizing our tool. So this is the experimental setup. The features used as input to the models were determined through the data analysis and the suggestion of the personnel. For each combination of the hyperparameters, models, both decision trees and random forest, were tuned and tested in order to find the best configuration. Here we see a table representing all the possible values for our hyperparameters. For instance, here we have the class misclassification cost, where we have the cost for the standard misclassification of the normal situation, then from the pre-end of life and end of life. A ladle-wise cross-validation was adopted. It is similar to standard cross-validation, but each time the data concerning one single ladle are kept for model validation, while the others are used for the model's training. Then, for the evaluation, the familiar recall and precision metrics are used. The recall is the rate of samples belonging to an arbitrary class that are correctly classified. Then the precision is the proportion of samples identified as belonging to a class for which the prediction is correct. So these are the tables representing the results achieved by the two methods, presented in numerical form. They are quite satisfactory, especially those achieved by the decision tree and those where the cost of a missed detection of end of life or pre-end of life are high, as expected. The recall for the end of life is high, almost 80%, with a satisfactory precision. And the precision is very high also for the standard situation. These numbers put into evidence the advantage of using this kind of classifier as the core of our decision support system. But we can appreciate it more in their graphical form that I show you now. This is a comparison throughout about 200 hits of the actual and predicted ladle status for two distinct ladles during the validation. Here we clearly see that the classifier is able to detect all the situations of interest. We also see that it is a conservative approach, as it tends to overestimate the danger. But that is not a big problem from the point of view. It is exactly what we want. We want to avoid the danger. So it doesn't affect the productivity. But if you see from this picture, we are quite satisfied by this kind of behavior. All this model that was developed on my PC in Python had to be integrated into the existing IT framework at Ferriere Nord. We did it by sharing a standalone service that takes from the IT infrastructure the suitable input. It performs all the feature structure extraction and so on, then predict the status of the ladle, which is currently handled as a traffic light: red standard, orange pre-end of life, and red end of life. So do the maintenance. Then these information are shared on the GUI, on the graphic user interface, through colors, and more information can be obtained by clicking on the interfaces, mainly to see the values of the predictor inputs. So, conclusions. We show how the developed decision support system for automatic assessment of ladle status during production can be put forth. This DSS learns from plant data and achieves good results. It can advise with satisfactory precision about the ladle end of life and pre-end of life in the context of predictive maintenance. So it can substitute or can be put aside of the human operator, increasing productivity, product quality, and limiting the danger related to the ladle overusage. Now it is part of a real steel plant where new data and situation are collected, and it is possible to continuously improve the classifier, updating the classifier by using these new data that also represent different situations. In the future, it is possible that to use more data coming from the cameras, or more data coming from different databases, or maybe using different human operators that put their opinion in the database. Then we will have a wider span of data, wider different kind of steel. And it will also be possible to consider more complex classifier. For instance, we can go deep. So using different kind of neural network, deep learning, and so on. It will also be very nice to have a simulator for using reinforcement learning in this context, but maybe it's really the future as the car I show you in this picture represent. It was the end of my talk. 28 minutes. I think I am in time, and I also have time for a couple of questions. Thank you.
Marco, I have one question.
Yeah.
Birgit. I was just thinking, when putting this algorithm into operation, do you always need infrared camera data, or is it also possible to do without an infrared camera?
Currently, the infrared camera information is needed by the classifier, but also from a computer science point of view. It is an input that is needed. It is possible also to provide a sort of fake data from the thermocameras to make it work, but in that case, the prediction would be less reliable. It is possible, by the way, to construct a side of this, let's say, complete classifier, a less complete classifier that is trained, that is created, not exploiting the thermocamera's data. And in that case, if for some reason the thermocamera's data are not available, we can switch to this other classifier and see what happens. I expect it to be a little bit less performing, because thermocamera data are quite important, but we still can get an information about the status in case of malfunctioning of the thermocameras or something like that.
Yeah. I mean, some steel plants already have infrared cameras, some don't. So it's always a question of
exactly.
Yeah, what's available, what everybody wants to invest. So okay. Yeah. Okay, thank you.
Welcome.
So we don't have more questions. Okay. Okay, then in this case, we will proceed with the presentation of CETIC from Gustavo on the steel plant simulation tool.
Okay. My name is Gustavo Spina. I'm research and development engineer in the CETIC. And this is the simulation tool we developed at CETIC for the TRACOT project. So in the first time we got a description of the steel plant by Feno with the different components and the furnace, the cranes, the ladles, and our idea was to model the function of the plant. So in the first time, we suppose we delimited the zone of the plant in which the ladle will be transported and processed, and define in each zone what is the process that can take place, and how long it takes, and constrain the zones with the number of ladle that can be processed at that zone. So the zone represent the process and the kind of task that is performed of the ladles in the plant. So so the specific zones for the processing are the furnace, the continuum casting, and the and the refractory zones at the end of each processing, and a special zone in which the ladle is put to start the processing or ending the processing. So in this picture, from this picture, we specify the constraint of the functioning of the plant. So the plant will function with a variable number of ladles, and up to 2 ladles are processing in the time at the plant. So so for each zone and process in the plant, we could estimate the times for each kind of processing according to the database of tracking data that was provided by FINO. So we could estimate each we could define a distribution of the processing time for each process, and calibrate the simulator with that with those data. So why we decide to use the simulation approach is essentially to reproduce the actual operation of the plants and be able to collect performance metrics in an uncertain using uncertainty information. So we can handle that uncertainty on the task duration, or on the ladder availability, or even on the reliability of the process. The process can the failure can be modeled with that approach. And then with respect to the optimization task, using the metrics that we are collected in the simulation, we can estimate the adequacy, or the we can estimate the adequacy of a policy, of a providing policy, or estimate how the performance metrics evolve with respect to the evolution of the input parameters, and then finally estimate how the ladders evolve in the plant with with a discrete model. So the components of the discrete event model. So the zone are represented by the storage and processes. So in a zone, the ladle is put in a storage, and then is taken by a process. The process take place with a given time. Some transformation of the ladle and the steel can be made and estimate, and then the process put the ladle into an output storage. So essentially, a processing with the ladle is modeled like that. And beside of that, the still providing is modeled with a special kind of process called provider. So in a given amount of time or when some condition can be met, the still can arrive in the plant. Voilà. So the events in the discrete simulation model are related to the starting or ending of a process or a providing process. So when the process starts, the input resource should be available. So in this case are the ladles and the steel. When the process is ending after a given time, the use resource transformer can be put into the output storage, and we can evaluate, see if the storage can overflow. So the storage has a given capacity, and depending on the type of storage, the process can be blocked, or the resource can be wasted if the storage overflow. So after each event, the simulator verify that the activation condition for new events can be checked. So so for instance, when a process starts, always the ending of the process can be triggered, or at the end of a process, the storage state are updated, and is possible to check if another process can start at that time. So in each event of the simulation, the metrics can be computed and updated, and essentially the metrics are bound to the storage and the process. So finally, the flow of the resources in the steel plant are represented with these simulation models with the special storage when the starting ladles are bought, and a steel provider with a given policy, and the different processes and storage representing the processing of the ladle in the plant. So so to configure the inputs of the simulator, we specify the number of ladles. We define the distribution of the process duration, what is were inferred from the ladle tracking. Also, we define the horizon time of the simulation, which is the number of days in which we will simulate the function of the plant. Essentially, that can be 1 day or 1 week. And also the important thing is the specification of the providing policy. So how often the plant will be provided with steel. For some processes, we can specify the percentage of failure, or to handle the uncertainty situation of some failures, and if we want to perform several simulations, and evaluate the average metrics, we can specify a given number of simulations per policy. In the output, we show the traces of a single simulation. That means in each time of the simulation, what happened with respect to the process and storage. At the end of the simulation, of every simulation, we compute the basic metrics. So how many lattice were processes by a process in which time. And and for the whole simulation, we can compute metrics for the energy consumption with respect to the basic metrics. So so we finally implement this with two web services. One to perform the single simulation and the other one to perform the several simulations according to the still policies, and a given number of simulation per policy and number of ladles. In this way, we are able to compare the metrics with respect to a given number of ladles in the plant and a given providing policy, and estimate what policy has the best metrics after after aggregating the simulation. So so this is this is what we do with the simulation tool, and we use the OSCAR DS library. So it's a part of a operation research library we developed in the SETIC. So I will give the I will give the turn to Renaud, or
Yeah, to Renaud for presenting the library.
Okay, so
Right.
As Gustavo mentioned, this work has been done using the OSCAR, the module of a module of that a simulation module coming from the OSCAR library. So first of all, OSCAR was meant to solve optimization problems. So these are typical examples of optimization problem. So here you have a drawing that illustrates what scheduling problems are. So like task and precedence and limited resource, or routing problems, okay? Where you have vehicles that have to reach a set of points and minimize the distance that is spent on the road, right? So these are typical combinatorial problem, combinatorial optimization problem, and OSCAR is a library for solving this kind of problem, and it includes two state-of-the-art optimization optimization engines. So one is CP and the other is CBS, and it also includes a discrete event simulation engine. That's the engine that has been used by Gustavo in the context of this project. I forgot to mention these are all developed in Belgium. It started in 2012, and it's a collaboration between SETIC, UCL, that's a university close to here actually, and Insight, which is a spin-off from UCL. So in this project, we use the discrete simulation engine. So roughly speaking, discrete event simulation is a method to evaluate statistics on a modeled behavior using typically Monte Carlo approach, and it's very scalable and expressive. So roughly speaking, what is in under the box is that you have a model and a model that is with probabilistic behavior, and you will run the model many times and extract statistics out of this run. So typically you can collect average, worst case, percentile, etc., and MTBF, globally speaking, starting from individual probabilities of every statistical behavior that is encoded in the model. So we have a very fine-grained model, and out of that we can extract a global statistic about the behavior of a whole factory in this case, okay, like a throughput out of MTBF, for instance. So this is roughly how the simulation engine performs. I'll run it again. So it will execute the model many times, okay, and each run might be different from the other one because there are probabilistic behavior, and when it has executed the run many times, it can build statistics, extract statistics, observation out of these many runs. And this is the typical Monte Carlo approach. So there is another, so I will now briefly present two other engines that are available in OSCAR. So these are not simulation engine, these are optimization engines. So the first is local search optimization. Okay, so this will find a solution to an optimization problem, so that's different from simulation, where we just want to evaluate something. So here we want to optimize something. And so this approach is very scalable and expressive. So roughly speaking, when you have an optimization problem, you have many solutions. Typically, you have more solutions than the number of atoms in the sum of this kind of crazy metrics. And local search proceeds in a very simple way. So you pick up an initial solution, which is can be either random or built with a heuristic. So typically this can be a planning for a steel plan, okay? And we will try to improve it using small heuristic, like moving something earlier in the planning or later in the planning, and see if this improves the planning. And if we find something that improves the planning, then this is the new planning. And then we repeat this process of finding a small improvement and repeating this improvement. So while this looks like very dumb, it achieves very good speeds. I mean, it achieves to deliver a result within an acceptable amount of time. Okay, so this is pretty interesting when we face a problem with many possible solutions. So you have a decent response time. So this is the basic idea of local search, and this can be enriched using black magic, well, things that I used to call black magic, but in the academic community, these are called meta-heuristics. Okay, so roughly speaking, it's the same. Meta-heuristics is techniques that will ensure that the optimum found by the local search is of very good quality. Roughly speaking, that's ID. There is another model, another search optimization engine that is the constraint programming engine, which is developed at UCL. So this is a very different behavior principle than the local search. So this will perform an exhaustive search. So if you optimize something with constraint programming, you have the optimum. It's a proof of optimality. It's not possible to find anything better. So this is called a complete algorithm. Okay. It always finds the optimum. So if you want to find the optimum planning for a steel plan, you could go with constraint programming. Then you have the optimum, considering that your data are not noisy, which is never the case. But it has much less scalability. Okay, so roughly speaking, how the constraint programming works. So you have here the search space, which is the set of all possible solutions. So remember the cloud with many dots in local search. In constant programming, you represent them all symbolically with bounds, minimal and maximal value for each variable, these kind of things. Minimal start time and maximal start time for each task. So symbolically, we can represent many possible schedules with that. And constant programming will use two mechanisms. First, it will split to perform some arbitrary choices. Like, okay, we will make this batch before 10 a.m., for instance, this batch of steel. That's an arbitrary choice. So there are two possibilities. Okay, either we do it before 10 a.m., so that's the left part, or we will do this batch after 10 a.m., that's the left choice that you see on the screen. Okay, so given this choice, we first explore the left-hand side. So we have an arbitrary choice, and then we'll see what kind of quality we can reach with that. Okay, so the power of CP is that it can exploit this arbitrary decision to restrict to propagate this information. That's if we decide to make a steel batch before 10 a.m., then other decisions can be deduced from this information. Like some other batch have to be shifted later on, etc. So this is called propagation. So this will restrict the number of possible combinations. And this process of splitting and cutting the corner, called propagation, is repeated in a recursive fashion. So this will actually explore a full tree. And sometimes there is no possible solution in the concept of search space. And then we do backtracking. We go back to the previous state and we explore the left-hand side, the right-hand side, and eventually we can find a solution, and we are happy with that. So this is a very a more time-consuming approach that can find the best possible solution, but scales much less than the local search approach. Yeah, that's all. What I wanted to say is that there are other modules in the OSCAR. Besides the DES, we also have the local search, which scales to large size problem to perform optimization, and the CP engine that can find optimal solution for combinatorial problems. So OSCAR can be downloaded, it's open source, and that's all I have for you today.
And of course, the disaggregation stimulation with the factory modelization also made by Reno.
So, if there are any questions on the simulation engine and the OSCAR library that was presented by Gustavo and Reno? No? Okay. Okay. In this case, I will finish presentations by presenting a few more solutions. Some of them we also used in TrackOpt, solutions for the steel industry that we are developing here at CETIC. So one is... Oh, sorry, I'm not sharing it.
Be careful with the button of sharing is beside the button of leaving, so don't leave. Share.
Okay. Yes, indeed. Okay.
Yes, to the presentation.
Thank you.
Yes,
Okay.
and now you can start fine.
Okay. Apologies for the screen sharing issue. So the first solution is FADI that we also used in TrackOpt. Is a framework for big data analytics. It's an open source. It's based on mature components and tools. It's infrastructure agnostic, quite scalable. We used it for data integration, for building data ingestion workflows, for collecting both stream and batch data, and also for data storage in time series databases, relational databases, and so on. And also for analysis of data based on PassSpark and other tools. It allows visualization and monitoring of the data and the results of the analysis. And we have also built a wizard for automatic deployment and configuration of FADI in order to make it more easy for deployment in plants and various environments. So in our FADI big data platform, we use the software factory architecture that enables both system developers and data analysts to define and develop high quality applications and components in order to build very efficiently data analytics workflows. We use the DevOps methodology and best practices for deployment, release, and monitor of the components and the models of the analysis models. We also are using cybersecurity mechanisms. So we have basically a DevSecOps for continuous monitoring of security aspects. And with some tools like Vaccine, we can also do automated countermeasures such as firewalls and parts of the system quarantining. Here at CETIC, actually it's 2 rooms next to us. We're sitting now. We have a server room with a lot of machines like this, and we can deploy on premises FADI and the FADI cluster and build test beds for the plants in order to test the workflows, the machine learning workflows before deploying at the plant. But we also can do that in a third-party Kubernetes cluster, cloud environment, where we can select also where the data center region is, so it can be in Europe. And we have benefits from that in terms of maintenance and scaling. Another applications or system we have developed here at CETIC is for process monitoring and time series information monitoring in order to monitoring and also analysis and detection of anomalies. It is very helpful for synthesizing the information and simplifying and facilitating the machine learning operations. And finally, I would like to present another solution that we have developed at CETIC, which is the dynamic mapping gateway for integrating various IoT and robotic devices with different interfaces and data to the edge and to the cloud and to the platforms like ThinkSport for monitoring IoT devices or time series databases like, for example, T-Storage. So these are some tools that we have developed here at CETIC. Some of them we have used also, FADI, for example, we have used also in TrackOpt. Yeah, thank you very much. If you have any questions from my presentation or any other topics to discuss regarding the project, the solutions that we have developed during the project and the other solutions we have presented.
Thank you, Nicolaus, Gustavo, and thank you all, Birgit and Marco. Now we are perfectly on time, so now we have considered 30 minutes for open discussion. If there is something to share or still some questions, we have time to do this. So if anybody has a question to our speakers or just want to share some thought or seems that no questions, so you have been all perfectly clear.
Maybe shall we stop the recording now?
Yes, yes.